Yes, imaginary numbers are not imaginary. And I am damn sure that hardly anyone understands what the hell this I, or which is equal to the square root of a negative one is. Therefore, after watching this video, you will never call I as an imaginary number. And before we start, let me ask you a nice geometry question. We have an equilateral triangle whose center is at the origin or 0, 0, and whose this vertex is at 2, 0, that is on x-axis. Now, our job is to find the points of the other two vertices. Let me tell you that we will be solving this question at the end of this video, and that too, using imaginary numbers. Yeah, you will see a real-life application of this I. So stay tuned. Now, the first question that comes to mind is, where did I come from? Let us learn about I algebraically. Consider the equation x squared plus 1 equals 0. Now take 1 on the right side to make it x squared equals minus 1. Now take square root on both sides. We get this as x and this as plus minus square root of minus 1. And what is this? Yes, it is I. So x equals plus minus I. Now let me tell you that 99% of people stop here because they either don't know or they don't care about I anymore. They are like, what are we supposed to do with it in real life? It doesn't even make sense. And this is where they make a big mistake, because it is where the real fun begins. First, think about how we look at numbers. Numbers are something we use daily, like counting money, measuring distance, or tracking time. We mostly see them as quantities. Now imagine a number line. It's a straight line with 0 in the middle. Positive numbers and negative numbers, right? We can intuitively think about positive numbers and 0. But what are these negative numbers? What do they mean? For example, think about money. If you owe someone $10, you could think of it as having minus $10. It shows that you're in debt or below 0 in terms of money. I hope you are not. So, this is one way of thinking about negative numbers. But here is where the cool thing happens. Assume we have a positive number 3. Now, if we multiply it by a negative one, we all have learnt this in school, that it will become negative 3. Like imaginary numbers, most of the people will think about this multiplication as a simple multiplication between two numbers. But what really happened? We were in this direction when we had 3, and then, after multiplying it by a negative one, we moved this way in the opposite direction. So, multiplying a number by negative 1 in one-dimensional case implies that we rotate that thing by 180 degrees. Also, it works both ways, which means if we have this negative 2 here, multiplying it by negative 1 means we are rotating it by 180 degrees to make it 2, right? Now here comes the magic. Let us enter into two dimensions. Suppose, now instead of rotating this 2 by 180 degrees, or multiplying it by a negative 1, what if we want to rotate by 90 degrees? This is where I comes into the picture. We can multiply the number by I, and we get 2 times I. So on this graph, if this is real number line, and if this is complex number line, we get here 1i, 2i, 3i, and so on, and on this side we get minus 1i, minus 2i, minus 3i, and so on. So, after rotating this 2 by 90 degrees, we reach here, which will be 2 times I. And now, what if I want to rotate it by another 90 degrees? It will be 2i times 1 more I, or 2i square, which we know is minus 1, as I square is negative 1. So, we see that this thing becomes the same as multiplying by minus 1 and rotating it by 90 degrees twice, or 180 degrees. So, I is not simply an imaginary number, it is a way to make the number two-dimensional instead of a single-dimensional number line. Don't you think this is super cool? And we can have tons of applications for this thing in real life. Now let us draw a circle of radius r like this. So, if we have a point here, and let us rotate this point by an angle theta. Then this length will be r times sine of theta, and this piece will be r cos of theta, right? So this point will be r cos theta, comma, r sine theta, and in our complex plane, or in this graph, we can represent this as r cos theta in the real number line plus r sine theta times I in this imaginary number line. Take r as common, and we get r times cos theta plus I sin theta. Now we can use this Euler's formula without getting into much technical details. This thing will become r times e to the I theta. Also, this r can be written as r plus I times 0. Thus, this point can be obtained by taking this point and multiplying it with e to the I theta. Note that theta will be positive counterclockwise sense, and it will be negative clockwise. Now consider the question that we asked at the beginning of the video. It's time we apply whatever we have learned and solve it using imaginary numbers. We have this equilateral triangle whose center is at the origin or 0, 0, and whose this vertex is at 2, 0, and we have to find the other two vertices. Now put this triangle on this complex numbers graph. Since this is an equilateral triangle, therefore the center of this triangle will be the same as center of the circumcircle of this triangle, or the circle that we draw like this, and it will be at origin. Now you can see where we are leading to. An equilateral triangle has 3 equal angles of 60 degrees. So, the vertices are evenly spaced around this circle. So, if you start from one vertex, the next vertex will be 120 degrees away. Thus, all of these 3 will be 120 degrees. So, what will be this vertex? It's simple, right? Theta will be 120 degrees, and thus this vertex will be 2 plus I times 0 times e to the I times 120 degrees. So, it will be 2 times cos 120 plus I sine 120. 2 times cos 120 is minus half, and sine 120 is root 3 by 2, and thus it will be minus 1 plus I root 3. Or it will be simply minus 1 comma root 3. That was simply awesome! See, using imaginary numbers, we have obtained this vertex so easily. Now tell me in the comments, what will be this vertex? Also, it takes a lot of time and effort to make these type of content, so if you like and share it, then it will simply make my day. So good!